Okay, we are on page 14 today, and we're going to talk about graphing from factored form. When we looked at quadratics the first time around, and then when we did our 4 function forms of a quadratic little kind of review unit, refresher unit, earlier this semester, we talked about key features that we can see from factored form. We didn't do very much graphing just from factored form, though, particularly in our 4 function forms unit, because I made you find all of those equation forms, those function forms, so you have the others to rely on as well. So today's going to be a tiny bit different in that we are going to graph only using our factored form, but the information that we get from factored form should be familiar, and we have written equations from factored form before, so that part will be familiar as well. Now remember that factored form tells us the x-intercepts. Remember that these can also be called roots or zeros. So on Delta Math or Khan Academy, you may have seen find the zeros of the function, find the roots of the function. That all means x-intercepts. Okay, so we're talking about the same thing there. It looks like y equals a, which is my lead coefficient. Remember that tells me the shape of my graph, how we open, if I go out 1 and up 1, or out 1 and up a half, or up 2. And then x minus m times x minus n, where m and n are the x-intercepts of our function. One thing that we didn't focus on so much in our original quadratics unit is the relation of the vertex to the x-intercept. Now we know that parabolas are symmetric with the vertex in the middle. That means if I have a point here on this side, I've got a point here on the other side. What that also means is that the vertex will always be halfway between the x-intercepts. So let's say these are my x-intercepts. The vertex is halfway between them. So this distance and this distance are the same on the coordinate plane. So let's take a look at graphing some functions from factored form. Now, because we have factored form, that means we know the x-intercepts. So I'm going to start by identifying the x-intercepts. My x-intercepts for 1a would be -1 and +1. Remember, anytime I'm swapping between a feature on the graph and my function where I'm in parentheses with x, those signs swap. So this means I have an x-intercept at -1. This means I have an x-intercept at +1. Okay, I'm going to go ahead and plot these. So -1 and +1. Something we talked about in our previous quadratics units is that if you were to throw parentheses around this, you no longer have x-intercepts. As soon as I put parentheses around that, it's not a list of x-intercepts. It's now an ordered pair describing a unique point on the graph. So this would be that point right there. That's not what I want. That's not on the x-axis. It's not an x-intercept. So make sure we're not putting parentheses around these things. I'm going to go ahead and erase that off my graph there. So I've got my x-intercepts plotted. If I look at my lead coefficient, I don't see anything there, which means it's just 1. So that tells me my parabola should open up and it should have the same shape as my parent graph. So from the vertex out 1 and up 1 to my next pair of nice points. Now we know that the vertex is halfway between our x-intercepts. So halfway between would put it somewhere on here. So now I'm going to sort of reverse engineer that shape of the parent graph, that out 1 and up 1, to figure out where my vertex should go. Since my parabola opens up, I know my vertex should be down here. These are both out 1 from where my vertex should go. That means they should also both be up 1 from where my vertex should go. That means my vertex has to go here. That's the only place where I can put it, where these 2 points are out 1 and up 1 from the vertex. Does that make sense? That's kind of backwards of what we've done so far, okay? And then I'm going to go ahead and find my next 2 nice points. Those would be out 2 and up 1, 2, 3, 4. So we're kind of reverse engineering 1, 2, 3, 4 our graphs here a little bit. For B, I'm going to start again with my x-intercepts. So that would be +1 and +3. And I'm going to go ahead and plot those, +1 and +3. My vertex is going to be halfway between, so it's going to be on this line somewhere on here. My lead coefficient is -2. That means that this graph is going to open upside down and be stretched by 2. So from my vertex, I would expect to go out 1 and down 2, since we're flipped upside down and we're stretched. Now these points are both out 1 from where I know the vertex should go. That means the vertex also needs to be up 2 from where those points are. Does that make sense? Again, this is a little bit backwards from how we've used that lead coefficient before. And then to find my next nice points from the vertex, out 2, and normally it would be 4. We have to double it because of our 2 in front, because of that stretch. So it would be 8 instead of 4. 1, 2, 3, 4, 5, 6, 7, 8. Out 2, 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to go ahead and connect my points so I can have my sketch of my parabola there. Questions for me so far? Okay. One thing I do want to point out while we're talking about these, on some of your Delta Math graphing assignments, the directions say that you must include 5 points on the graph, including the vertex and the roots. So that means when you plot points on there, they want to see the vertex and they also want to see the x-intercepts. Even if you could fit your 5 points down in this section of the graph or up in this section of the graph, they want you to click to plot points that are the x-intercepts, that are the roots or the zeros of the function. Okay, and I know that tripped a couple people up, so I just wanted to bring that up as we're graphing by using the x-intercepts today. For C, again, I want to start by identifying my x-intercepts. What are my x-intercepts for C? 2 and 6. Very good. 2 and 6. So I'm going to plot those. 2, 3, 4, 5, 6. I know my vertex should be halfway between these, so it should be somewhere on here. We could call this line our axis of symmetry. That's not something we focused on when we did our quadratics units. It's not something that we're going to worry about a lot in Algebra 2 either, but there is a name for that line. Now I'm going to look at my lead coefficient, which is just 1, to determine the shape of my graph. Since it's positive, I know this will open up. And since I don't have a stretch or compression, I know we'll do the same shape that we had for A. So from the vertex out 1 and up 1, out 2 and up 4. Now, if I look here, these points, my x-intercepts this time are out 2. That means that they have to be up 4 from the vertex. So my vertex would be 1, 2, 3, 4 down. That makes sense? Since they're out 2, they have to be down. They have to be up 4 from where the vertex is. And then I can fill in those other points that we expect to see, out 1 and up 1, to get the shape of my parabola. And don't forget to sketch in your graph. What are my x-intercepts for D? Yeah, this guy gives me 0. The only thing that I could have in parentheses with x and not have to write it would be if this were x minus 0 or x plus 0. Since it's 0, the plus or minus doesn't really matter. But the only number that this could be, the only value we could have here would be 0. So my x-intercepts are at 0 and -2. I'm going to go ahead and plot those, 0 and -2. Again, we are looking at our vertex halfway in between our x-intercepts. Since these are out 1, that means that my vertex, based on our lead coefficient, which is just 1, should be down 1, right? Since our lead coefficient is 1, we're the same shape as the parent graph, we're opening up. My next points then would be out 2 and up 1, 2, 3, 4. Out 2, up 1, 2, 3, 4. And again, don't forget to sketch in your parabola. Questions for me so far? Okay, a little bit different again than how we approached most of our graphing, but hopefully not too bad. The next thing we're going to do is write functions in factored form from a graph. So when we looked at vertex form last time, we started by graphing from a function in vertex form, and then we started with a graph and created that function. So same idea here. I did this one way, now we're going to do it the other. I'm going to go ahead and turn the page. And we've got a few graphs here. We're going to go ahead and write a function in factored form. So we did vertex form earlier. Now we're going to do factored form. Okay, so I would need to know where those x-intercepts are. My x-intercepts here would be at 6 and 8. So that means when I go to plop these into factored form, I would have x minus 6 and x minus 8. Remember, when I'm going between function and feature on my graph, if it's in parentheses with x, I'm going to see a sign change there. I'm going to see opposite signs. And then the next thing I need to know is, what is that lead coefficient? So we actually do need the vertex for this. Normally I go out 1 and up 1, but here we go out 1 and down 1. So that means our lead coefficient would be -1, or just a negative sign in front there would be fine. And don't forget your y equals. So y equals negative x minus 6 times x minus 8. For B, again, we're going to start by identifying our x-intercepts. So that would be here at -3 and here at +1. So the factor part of it would look like x plus 3 times x minus 1. The order of your factors is not important. So if you wrote this as x minus 1 times x plus 3, that's fine too. And then I'm going to use the vertex to help me determine my lead coefficient. This is opening up, so I know my lead coefficient is positive. But as I go out 1, I do not go up 1. When I go out 2, I go up 2. So that means my lead coefficient would be a half. I should go up 4. I'm only going up 2. I've cut that distance in half. So I would have y equals 1/2 x plus 3 x minus 1. Or again, if you had the order of your factors swapped, that's fine too. Questions for me so far? Again, this is something that we did when we were looking at swapping between our different function forms and being able to write a function from a graph. If I didn't have a nice vertex, but we had nice x-intercepts, we wrote a factored form. Let's take a look at C now. My x-intercepts are here and here, so that would be -2 and +2. That means the factored part of it would be x plus 2 times x minus 2. And then if I look at the shape of my graph, they didn't give me grid marks here, but I can sketch them in. So it looks like to get from my vertex to my first pair of nice points, I go out 1 and up 1. That means my lead coefficient would just be 1. So y equals x plus 2 times x minus 2. If I want to throw the 1 in front, that's fine as well. I would like you to try D now. What are your x-intercepts for D? Just the x-intercepts. +3 and -3. So my factors should look like x plus 3, because I have -3, and x minus 3, because we have +3. What's our lead coefficient on this? 1. Yeah, from the vertex to my first pair of nice points, out 1 and up 1. If you want to write the 1, that's great, but you don't have to, as we said with C. So you should have had y equals x plus 3 times x minus 3. Question for me on D? Okay. The last couple I want to look at, we don't have a graph, we have a different version of our function. So for E, we have a table here. We talked about writing vertex form from a table. We said identify the vertex from your table and then use the y values to determine the shape. Now we want to write a function in factored form. So instead of worrying about the vertex to start, we want to worry about the x-intercepts. So I can identify the x-intercepts of my table by looking for places where the y value is 0. So that would be here and here. Those are my x-intercepts. If I were to plot these on the graph, I'm going to go out on the x-axis, right, to 8 and 10, wherever those would happen to be. But we're not going up any. So I know that these are my x-intercepts. So I know my function would look something like x minus 8 times x minus 10. Now we're going to bring the vertex in to take a look at what that lead coefficient should be. So last time we talked about the idea that if I know where my vertex is, which we follow the repeating y's into the middle, and there's my vertex. Okay. If I look at that y value for my vertex, and then I look at the y values on either side, these y values are bigger. Okay, so that means if I'm just talking about where I am on the y-axis, we're starting with a y value of -1. And then as I move out from the vertex, right, by 1s on the x, so I went wherever this is, 1 in either direction. I also went up 1 to 0. Out 1 and up 1 means our lead coefficient is just 1. So that would be our function there. X minus 8 times x minus 10. And then finally for F, this is sort of a preview of what we're going to get to. We've got a standard form function here, and we want to write it in factored form instead. This is something that we practiced a lot in our quadratics unit, so this should be familiar. What we need to do to change from standard form to factored form is to factor our quadratic function. Remember, we always start factoring by looking for a greatest common factor, a GCF. Do I have one here? No, there's no value that I can divide all of these terms by. And then we want to look at our lead coefficient. And if this is a number that wasn't a GCF, we would have to use AC method. Since I don't see anything here, my lead coefficient is just 1. We can look at factors of -4 that would add to 3. We don't have to use AC method on this one. What numbers would I want that would multiply to -4 but add to 3? Yeah, 4 times -1. So my factored form here would be x minus 4, plus 4. These are not values I got from a graph, so I keep the signs the same. X plus 4 times x minus 1. Questions for me for today? Okay, so that's our little review of factored form. Next time, we're going to talk about graphing from standard form. So we're going to look at strategies we can use mostly to rewrite standard form so that it's something a little friendlier to graph. We're also going to do a couple more practice problems on factoring.